Okay, so that should be it. So okay, I'm gonna share screen to present this. Or should we? Do you think we should wait for other people? Or
maybe a few minutes.
yeah, okay.
Couple of maximum 5 minutes, but I wouldn't, spend
Right.
more than. I mean, you can start because Gerd also has to leave and things like that. And
Yeah.
we want to keep it within. Like last time, we keep quite good time. I think like little over 2, but like that, 2 hours plus or minus, or the most.
Yeah, I don't think it's going to take 2 hours.
Yeah, that will be good because we are anyway going live, and also you said every time the link is new, so we have to keep track of that.
Yeah, for real. So just check that we are indeed live. Have you done that? Have you gone onto YouTube to watch the stream? Sorry.
Yeah. I sent that the first phase. It's YouTube. It is there. I think I don't know whether maybe. No, I posted that after I watched that, but you have to go into search and look for that, and then it comes up, and then you go to the YouTube, and then because hi Christian.
Oh, Christian, right?
Okay.
Not sure. No, don't think so. No, so I was just checking the stream to see if it was running.
Oh,
there's a slight delay on the stream, so you were hearing yourself from like a few minutes ago.
Okay. So, I mean, this is not the same site that gives the YouTube. So it's a different site that it's, I think, recording to. But yeah, I put that.
Well, it's technically not recording, but do you have to sign in to Streamlabs or StreamYard, or do you just? Oh, you don't.
No. To get the stream, what we had, I think I can share the screen.
Yeah, go ahead.
Yeah,
because it's probably different from where I am.
Yeah, so I will share the screen where I saw our video. Let's see. Okay, so let me share that first.
Oh, do I have to? Yeah.
Can you see that?
Oh, okay. So that's what you see, is it? When you click the link?
Yeah. So what I did was, you see here, I put in the search. I think I put the search. The text.
The StreamYard link, is it?
The tags. Yeah. So I put tags, right? It says YouTube. You can see this, right? Text face. This was new. I mean, only when I put it like that, I saw this one. Then I clicked this one, right?
No, so I can see something there. That must be the old video.
Now it comes up.
That was our last video.
Yeah, the output. Yeah, it's an output video. So they are doing now.
Yes, I see
a
black box.
Okay.
Phase 2 first physics live stream session.
Right, that was the last one.
And then I forgot to put like our thing.
Yes. Now I'm seeing
our thing.
Yeah. Well, today's video is titled "Imputation of Missing Data in SDSS Reveals the Inhomogeneous Universe." So you can't see that title anywhere, no?
Maybe.
Okay. Yeah. So yeah, I thought you were able to switch it.
No,
so
I'm not.
I think I can change that. Is that a different one? Yeah. Yeah, it is.
I have uploaded 3 just for demoing, and
all the has given the circuit, and the circuit is so it seems to come.
No. this is just something.
So all the things, so these
That's
seem to be fine.
Good points.
So I can stop sharing. So what I'm saying is that I can probably stop sharing, right?
I think so. I'm not entirely clear.
So essentially,
on
you know, yeah.
What you see when you sign in. Is it just YouTube?
Oh.
Yeah.
Yeah, actually, I had to put search because the URL is not the same as the URL we are using now. StreamYard URL, that's stream.com-p gy, whereas the other one, the one that we are getting the output where we actually can see, everybody can see, is a different URL, youtube.com /watch, you know. So that's the URL we are seeing, you know.
Well,
you see that when I go back here, so you see that. So I put, you can put text like that, and then it will, you can see, can you see this, what I am putting now?
Yeah. Yes.
Well,
okay.
I can see about 8 different icons. One that says YouTube.
Yeah. The first one says text phase 2 first physics live stream session.
What I see is women at NA or something.
No, yeah, but that's just from the
Mail small business YouTube Arizona Corporation.
A review.
Can you see now? It's reduced now. Can you see now?
No. I'm not sure.
Maybe
you're looking at a different window, or maybe StreamYard doesn't let you show that.
Okay. So I'll put it in the middle. Sorry.
No problem.
So yeah, now I see the problem. Yeah. Okay. So I will. I have to find a common thing. The search here, I'll put there. Can you see the search? Let me see. Oh,
no.
Oh, here I can see only this much.
Okay, yeah, I'm just back to the YouTube sort of screen there.
So let me see. I try to put it here. I try to put are seeing only that. So I have to.
Well, I might be able to give you the login information for StreamYard.
I put in one of our emails. Yeah, I put in. Yeah, I put in one of our. Let me try to copy this.
I did not log in. I only put in the link. Yeah.
Okay, cool. Oh yeah, I'm just confused as to what it looks like on your end. You're in StreamYard, obviously. That's the website. So, but you can see me and hear me.
Yes.
So, okay. Well then, I think we're good to go. I might as well start presenting.
Yeah. I'll again. Yeah.
Okay.
One is we can probably go YouTube. Oh.
Okay. You're glitching out a bit, right, John? I don't know why that is.
Now I'm out. Yeah.
You're just sort of clipping.
So actually put in the email again. Now?
No, you're currently not sharing your screen though. No.
Yeah, I'm not sharing because
okay.
I'm going to put this URL in the email.
Oh,
so
I see.
We will see because the new one again goes somewhere. So I'll put what I will do is I'll put the URLs for our previous ones, the present one, and the last one, and the present one. So I'll try to put that as a list. Hopefully people will see that. I already put that in one of the...
I think if you were to put older links, it might get confusing. Just try and upload the most recent
just
link.
the general link, not all of them.
Okay.
I'll just say, if you want to get the phase 1, you get this one. It's a general one where you can get all the other things. It's a general URL. It's only one URL. You go there, you can get all the list there. And then last one, because each one now is going to be different. So each time I will update that, and then the list will grow a little bit, but not.
Okay.
But I think it's good to put that list.
Okay, I'm going to try and share screen.
Oh, go ahead.
But I just want to test this out to make sure it works. Way down. Can you see anything? Can you see neural network?
Yeah, neural network.
Imputations of missing Sloan Digital Sky Survey. Okay, what if I go into full screen? Can you still see it?
No, it's
no.
Not to be seen.
What do you see? Just the same thing you always did?
Right now, not only us. Only.
Okay. So obviously it doesn't allow for that.
You must share the whole screen, then it will work.
Oh, I think that's what. Do you know what? So you were able to see something, were you?
Yeah. Before.
Oh.
Can we edit? We cannot edit this, right?
No.
Because we don't want these.
Maybe. Okay, maybe I see what you're saying. I see what you're saying now.
The first 10 minutes we are just talking, and I don't know whether everybody need to see it.
Yeah, understood. But I need to. To be fair, I do need to figure this out.
It disappeared. If you share the whole screen, then you can show it. Not only the program or the application, the whole screen.
Yeah, that's fine. I didn't see that as an option in the original. So let's see. Let's try this now.
Oh, yes. Okay.
Better?
Yeah, it's good. Yeah.
Okay.
Good.
Great.
Right. So this is, as it says, neural network imputations of missing Sloan Digital Sky Survey data reveals the inhomogeneous nature of the universe and reaffirms the Great Attractor. So we'll get into it. First, do a little bit of background maybe on the Sloan Sky Digital Survey itself. The Sloan's Digital Sky Survey, began in 2000, and its legacy period lasted around 8 years. At the time, the SDSS telescope represented the largest digital camera in the world. There it is there, and was capable of taking up to 640 spectra simultaneously. This advancement allowed for the creation of a 3D color map of the universe containing potentially hundreds of millions of objects, including galaxies, stars, asteroids, exoplanets, and quasars. The map is divided into wavelengths of light: ultraviolet, green, red, infrared, and Z, which is the main redshift band. These spectral redshifts give a depth dimension to the otherwise two-dimensional photometric sky surveys. The optical colors of galaxies can also be used to relate the age of stars contained within them. Redder galaxies tend to have older stars, whereas blue galaxies have younger stars. In practice, we can quantify color in astronomy as the difference in magnitude between two different bands. There are two telescopes operating on the SDSS mission: the Sloan Foundation Telescope in New Mexico, I believe, and the one at Las Campanas Observatory in the Atacama Desert in Chile. So the main objectives of the SS project which is currently in its 5th generation, is to study the composition of stellar objects in the Milky Way, compositions, motions, and locations of distant galaxies, and the expansion history of the universe using different look-back times and spectra. To accomplish this, the SDSS project is broken into smaller projects, which include Apogee, BOSS or eBOSS, Marvels, Manga, and Segway 1 and 2, or SEGU 1 and 2. Apogee stands for Apache Point Observatory Galactic Evolution and is designed to measure the composition of the stars in the Milky Way. BOSS, or Baryonic Oscillation Spectroscopic Survey, and its extended version, eBOSS, are used to find the positions of galaxies and quasars. Marvels is a small exoplanet survey, which isn't really relevant to what we're talking about today, which was arguably not as successful as the other projects. And Marvel's comic book themed counterpart, Manga, uses tight bundles of fiber optic cables designed to overcome the limitations of taking spectra from inside of galaxies, which are normally shielded from view by copious dust clouds. So that's a bit of background there. This is an example of one of these 3D maps. Obviously, this is two-dimensional. We've got right ascension in the kind of theta component here and redshift going out. So this blue dot here is our galaxy. And then, as we can see, it goes out. And there appears to be these, one of the interesting features is the large-scale structures in this map of the universe. There seems to be concentrations of galaxies at certain points, and then goes the density goes down, and then it increases and so forth. So it's almost like kind of rings around our position. But another feature of this that is important is the fact that large amounts of the data is missing, owing to the fact mainly that our Milky Way gets in the way, so it blocks out certain portions of the sky. So the question is, well, the purpose of this research is to fill in the blanks, essentially, and fill in the missing galaxies. But let's see. So the next section is the homogeneous universe. Is the universe really the same everywhere? So part of this, in 1929, Edwin Hubble published his observational findings, revealing that the vast majority of stars, galaxies, and nebulae were redshifted with respect to the Earth. It was also revealed that the further these objects were from the Earth, the more redshifted they appeared. This curious fact led him to conclude, as several others did before him, including George Lemaitre, that the universe was expanding. Even more curiously, it appeared that the Earth was at the center of this cosmic expansion, an auspicious and odious position that it had not been privileged to since medieval times. Today, with our advanced knowledge of the Big Bang, we know that the Earth does not occupy any privileged position in the universe, and that each position in space is expanding away from each other like points on the surface of an inflating balloon. Just as the Big Bang has expanded space, our knowledge of the Big Bang has also been expanded by inflation theory, which is one of Alan Gouth's more enriching and bizarre theories. Inflation theory was developed in large part to solve inconsistencies in the Big Bang model, namely why the universe was both homogeneous, the same in all places, and isotropic, the same in all directions. The isotropy of the universe is predicated on the cosmic microwave background radiation, or CMBR, which is uniform to 1 part in 100,000 in all directions. In an interview with neuroscientist and investment banker Robert Lawrence Kuhn, Gouth explains how the universe could be inhomogeneous and yet still isotropic if it were surrounded by shells, but goes on to state that this is highly implausible and that no one really thinks that. When Gouth says no one believes that, he's of course talking about his fellow physicist colleagues. However, if we look at the literature, we see that a great many research papers have been written on this subject. For example, in 1987 and 88, Kuh and Cron published observational spectroscopic data obtained via the cryogenic camera spectrograph system at Kitt Peak North National Observatory, which revealed large-scale fluctuations in the redshift distribution of galaxies. In a letter to Nature dated 1990 from Broadhurst entitled Large-Scale Distribution of Galaxies at the Galactic Poles, physicists were calling for these results to be verified and for the implications for cosmology to be determined. In Astrophys Space Sci, J.G. Hartnett spoke of how an unknown selection effect simulates redshift periodicity in quasar number counts from the Sloan Digital Sky Survey. In a paper by Hartnett and Hirano, Fourier analysis of both the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey on the number of galaxies with redshift Z data results in galaxies preferentially located on co-moving concentric shells with periodic spacings. All of this strongly suggests that the universe is not homogeneous and that large concentric cells of galaxies do exist surrounding our Milky Way. We're still, for proponents of an isotropic universe model, is the discovery that not only is the cosmic background radiation anisotropic, but that its dipole is aligned with the orientation of the plane of the ecliptic and with the equinox points. This discovery was originally made by Max Tegmark in the application of Gaussian blur filters to images of the CMBR and has been confirmed by WMAP and Planck data. So those two space satellites that are out there. Well, Guth has explained this anisotropy with respect to the Earth's motion through space. It has been discovered that there exists anisotropy of cosmic acceleration in union to type Ia or 1A, supernova aligned with CMB dipole, which cannot be explained in such terms. The same multipole alignment has also been revealed in the large-scale distribution of spin direction with respect to spiral galaxies. So we can see here, this is a quadrupole, I believe, of the CMBR, and this line is the plane of the ecliptic. Some people, however, think that the alignment isn't really all that accurate because, well, in the previous slide, you can see they're kind of big blobs, blurry blobs. So where's are exactly the points? But if we look at this diagram, we can see that the equinox points are indeed aligned with the dipoles, like along the blue line here, which also goes through the south ecliptic pole, which is probably not too unexpected. And then the next equinox point goes through the other dipole and the north ecliptic pole. So that's kind of interesting. There's definitely an alignment going on. So let's look at conspiracy of data. So in my research, I was trying to recreate the image that we see before us here, or this image is slightly clipped. But while I was doing that, I was also researching other kind of effects. So in this article from the SDSS blog, the author discovered that the black parts of the pie chart are where SDSS did not map galaxies, either because our Milky Way is blocking the view from Earth or because those parts of the universe are not visible from our telescope in New Mexico. This information about the location of the telescope is curious, both because it was not mentioned in earlier SDSS videos from 2020 and because there are two telescopes operating on the SDS mission, as mentioned earlier, the one in Sloan Foundation and the one at Las Campanas Observatory. Surely the galaxies visible or invisible to the Sloan telescope would be visible to the Las Campanas telescope, given that they're in different hemispheres and vice versa. In any case, what this does reveal is that some of these pie diagrams are created from data which is completely taken by either one telescope in the northern hemisphere or the other, which tends to reduce the impact of the claim that these pie diagrams represent the entire visible universe, when the portion of the sky pertaining to the southern hemisphere must, by their own admission, be necessarily absent. So I contacted the SkyServer about this at the time, and I was asking how would I go about recreating this image, and I eventually figured it out for myself by the time they got back to me with their response. But well, the other interesting thing was then when I looked for this article, like, so as I was researching all of this information that I'm telling you about here, when I looked for this article, they'd taken it offline. So I had to back it up using archives based on, because it was still on my screen, so I could back it up. But I haven't checked to see why they took it offline. But I just thought that was interesting, but it's probably not a big deal. So let me think. Oh, yeah. So there are examples of other large-scale structures in the universe, such as these are called fingers of God. But according to research by Hartnett, this phenomenon is an artifact of redshift data and cannot be evidenced as concentric, or as he terms it, galactocentric universe model. So I just thought I'd include that. And then this was my attempt at mirroring the I can go back. Great. This is my attempt at mirroring or imaging the universe, and I had a couple of problems, as you see, but it also looks like there's fingers of God in this, but that could be something else. The main problem, or yeah, there's only one gap in this image, which is another issue. So filling the blanks, how to impute the missing data in the Sloan Digital Sky Survey. Once again, we see this image. This is just for reference. So our galaxy and the gaps. So my first attempt is sort of an artistic rendering. I just mirror the image and fit them together nicely. Then in the next image, figure 3, I try and use the clone stamp tool to kind of make it look less symmetric. So there's a certain amount of bias in this application. Like, obviously we can see there's definitely concentric rings going on, but so for instance here I tried to remove more data and just make it look, that was a kind of a decision I made that's obviously not based on anything in reality. Another example of an attempt at filling in the blanks was done by, I believe, Bernadette Chiardi, who's a project leader at MPA for the Max Planck Institute for Astrophysics. And we can see here that this bears very little resemblance to the earlier images we've seen. We've got Pavo Indus here, Centaurus, this is the Great Attractor, and our galaxy is here. So clearly, like, this is the imputated missing data here, and more of it over here, I believe. It's kind of hard to gauge where we are, but so the purpose that I should have mentioned at the beginning of using convolutional neural networks and neural networks to impute the data is to take out biases that people might have, because we can see here that there's no sense of any concentric rings here. So perhaps she left it out because such a thing, as Guth said, no one actually believes these rings exist. So what we want to do is impute the data using a non-biased neural network or a convolutional neural network. And the first one I've chosen is Deep Image Prior, which is Ulyanov, I think is his name, who invented it. Yeah, Ulyanov. Okay, so we can see here, excuse me. So initially I put in figure 2, which was this green image with the missing parts, and then impute the data. So we can see, yes, indeed, there are rings in this image, and there seems to be kind of a deeper green color here, where let's see, the bigger the size of the gap, the Deep Image Prior can't really impute the data very well. The certainty goes down, so that's what we're seeing here. Then we can pass this image back into a more defined model that deals better with data, and we can once again see kind of rings around the central galaxy, and in this case a very large blob of green here, which seems to suggest, which is located in the correct point where the norm Great Attractor is located. So that seems to be kind of a positive confirmation of something that's known about indirectly through things like dark flow, but is obviously not in doubt, but it's nice to see it reconfirmed in this manner, and seems to suggest that this method has some validity to it. So looking at the Great Attractor dark flow at the edge of the universe, we can see that it's located around here. So there's Pavo Indus supercluster. These are the voids that open up around it. And yeah, we have other Centaurus cluster as well. So it's kind of part of that. So the next part is to impute using an artificial neural network with a sliding window and polar transforms. So to do this, first we need to recreate the 3D map of the universe that I showed you, the green and kind of red circular image. And to find out where the gaps were, I had to produce these two graphs, but just looking for my notes on this quickly, might be this. So yeah, it is. So these are right ascension, and then the counts. We can see that there seems to, so this is northern hemisphere and southern hemisphere. So there's obviously more galaxies and objects in the northern hemisphere than there is in the southern hemisphere, which seems to be another kind of anisotropy. This is the end result. So I finally did manage to recreate the graph of all the galaxy positions. So the next step was to convert that to take away all of the grid and axis labels, and then store it as an image file, and then polar coordinate use polar coordinate transformations to sort of unravel the image to get this. So these are our gaps here that we want to impute. And so we need to find out the extent of those gaps, which I did by just counting the number of ones in the graph, which are equivalent to the background. And we can see that there's the most here and here. So between like 266 to 300 and 57 to about 114 on the other side. So those are the areas we need to impute. When we use a rolling window and a linear regression neural network, we see this result. So once again, we see like a fairly dark patch of galaxies in this area. So that seems once again to confirm the existence of the Great Attractor. Here's another example. Once again, quite a dark patch there. I've also imputed the other section in this graph, so you can see there's not much going on there. So that seems to suggest, we have a Great Attractor here and not as many stars over here. So I mean, well, if we look here again, these are them separated out, slightly different examples. So we have the Great Attractor, and then this area, which I'm calling the Great Repeller in a sense, but obviously not in any real sense, unless there's a lot of dark matter over there or something like that. But yeah, so you can see each time the program is run, you get slightly different results. So you can't use this to say, oh, there's definitely a star at this point or at this point. But we can use it to say, the density of stars in an area, maybe that could work statistically. You could also look at it from the point of view of structures. So like I said, there's a certain stochastic nature of the algorithm where things, the star points are different each time, but certain structures were quite persistent. So for instance, if we look at this, there's this sort of sweeping line that comes in here, and that appeared often, as well, this void here extended into this area a lot more than it didn't. And then we'd have like dark patches within this sort of dark purple oval that I have. So, and some of them looked quite like vortices. I didn't manage to capture the one that did, but you can kind of see, if you use your imagination, I guess they're kind of vortex-like. So it looked like there were two vortices there. So I was thinking of the idea that there might be these double vortices within the Great Attractor. It's just reminded me of the twin vortices that were postulated at Venus's south pole as well. So could a similar configuration of supermassive black holes exist in the norm Great Attractor on the far side of the universe is one of the questions I'm posing. So the limitations of the previous work was that both the CNN and ANN imputation do not directly contain Z-shift and right ascension data. It's more implicit because we're using a visual image to get that. So, you know, you're not gonna get Z-shift data if we're dealing with pixel brightness, basically. So in the future, we could overcome this in a number of ways, but well, the main way would be to use the data in the SDSS catalog instead of the image data. That would obviously give us the redshifts out of the box. Another thing that could be done is to employ an LSTM along with the rolling window for a better imputation. And this might be useful because, like, we could, if I go back, is there an imputation that works? Well, you could think like, here's a very dark or dense part of the universe, less dense, and then there's nothing over here. And then this is, you know, also less dense. So you could think of like, this is like summertime, maybe autumn, winter, and spring. So you could have a kind of a, how do you say, sort of temporal aspect to the universe, that the seasonal aspect in terms of data, you know, you have season and trend. So an LSTM might be useful for that. Then again, it might not be, you know. Also, it might be interesting to use James Webb Telescope to confirm locations of stars and galaxies, but obviously that's not, well, the reason why you'd use James Webb is because it tends to be able to see through gaseous clouds better to the stars behind them. But yeah, like I said, the imputation doesn't directly say where the galaxy is situated, so I'm not sure if that would be really that useful. And yeah, no, I'll continue on. So in conclusion, the Inpainting imputation provides an unbiased method of imputing galactic data and appears to suggest that the Earth or our galactic region is surrounded by concentric shells or great walls of galaxies. This provides a disproof of the homogeneity of the universe, just as the so-called axis of evil provides a disproof of the isotropic universe. I'm not sure if disproof is the right word, but it certainly calls it into question. So the artificial neural network imputations reveal a dense cluster of galaxies in the same region in which the Great Attractor is supposed to be located. This result is consistent over multiple instantiations of the imputation and constitutes an indirect confirmation of the existence of the Great Attractor itself. Along with the Great Attractor and its dense cluster, the imputation also reveals a region in the opposite direction, which is almost completely devoid of stars. This region could be dubbed the Great Repeller, although there is likely no direct repellent force involved, unless perhaps, as I said, dark energy or dark matter. Potential vortex in the region of the Great Attractor could suggest a supermassive black hole or sink in the region. So sink kind of from the point of view of John's work. Is there anything else there? Yeah, so that's it. There's the references. And yeah, thanks very much. So how do I exit that? Stop sharing.
Your Great Attractor resembles my model of event horizon, and the great repellent would be the particle horizon I showed in my last. You know the picture, or should I show it again?
Yeah, if you want to, yeah, do, because there's a number of different diagrams I remember you have. So,
moment. No.
So I had a lot of notes and stuff prepared for that, but I kind of went off track a bit halfway through, but that's no harm. So it didn't take long. It was less than 10. No. How long did that take? Oh, it's supposed to be started a bit late, but around half an hour, so it's not too bad.
Yeah. Yeah, it was overall a good thing. I mean, it points to something new.
Definitely. Oh, you think? Yeah, I suppose it, yeah, I mean, there's been people talking about this since the 80s, of course. Okay. But it's kind of a bizarre thing, you know, a universe seemingly centered on our galaxy, for one.
You see this?
Oh, yeah, I'm going to add that to the stream. Oh, yeah, I do see that. Yes. So,
okay.
Yeah, go ahead. Yeah, so what were you saying there? Is you have the event horizon and the particle horizon. It's almost like a what do you call this? Like the south and north pole of a magnetic field.
Mm-hmm.
Yeah, so you have. I see. So one is the attractor, one is the repeller. Oh, that's interesting. So the idea is that the entire universe has a pole, or like dipole.
Mm-hmm.
And so that diagram is not a space-time diagram. It's not showing like past and present or future. It's rather showing the Earth, the universe as it is in space, like in a static sense. Right. So that is interesting. Yeah, because I'm thinking about that. Like, I mean, you know, like if it is as it appears that there are these giant rings around our galaxy, then it would. And then when you include the, how do you say, the axis of evil in that, it even looks like the Earth might be more central to the whole thing than merely our galaxy. So it could even be more localized. Then you have the issue of like, then there's like a lot of things moving in one direction. So I was thinking, you know, there's these models of the universe where you have like a toroidal model. I think that's kind of close to what you're talking about as well, Gerd, in your work. So like, but this might be slightly different. So at the kind of like Emmanuel's horn torus, where you know, you'd have the Big Bang at the center, and then it explodes out, expands out, and then goes out and out, and finally there's the Great Attractor, like the big crunch, where it goes back in, and then it's constantly cycling around this sort of topology.
The particle horizon would be the place where the Big Bang is situated. Maybe.
And what about the so the event horizon then is the opposite end.
Yes.
Right. So it's kind of right. So that's why I use the term event horizon, because it's a bit like a black hole or something.
Mm-hmm.
Right. So in my like version, trying to look at the structures and understand what was going on, I came across two holes. You know, so there's like two event horizons, which I thought was interesting, and especially when you consider, you know, the mythology is very.
Yes, it's possible to have more than one event horizon. One, the biggest is from the universe as a whole, but if there is a black hole, there is another event horizon.
Of course, like any black hole that's just sitting out there in space will be an event horizon of a kind.
Mm-hmm.
Yeah, true.
Okay, Is it possible that you have a chiral type of black hole where one is left-handed, the other is right-handed?
Yeah, there is the Schwarzschild, isn't it? Radius and those Schwarzschild black holes, they rotate, don't they?
Please, but I must now finish because I have another.
Okay.
That's great.
Thanks. You. Goodbye.
Okay. Thank you. Yeah, we'll see you next time.
Yeah. Okay, that was great. So, just what I was saying about the two black holes. You know, if we go back to what was the word? Oh yeah, ancient mythologies. Yes, of different ancient civilizations. For instance, the South Americans believed that when people died, they went into space to this place called Xibalba, which I believe is in Orion's belt. So it's like Alnitak or one of those stars. But then there was also that was if you're a good person, I think. But if you're a bad person, you went to like the Crab Nebula or something in part. You know, it's part of Orion's sword. It's one of those anyway. So I thought that was interesting. You know, you could have this idea like you have these two vortices at the end of the universe, kind of. So like if you're bad, you go into one. If you're good, you go into the other.
Oh yeah. I mean, it's like a heaven and hell type of thing.
Yeah, exactly. Yeah. But then then Earth is at the center of the whole thing. So, you know, so that again, that feeds into a lot of ancient kind of mythologies of the Earth being stationary. So that was one of the kind of things I spoke of in future work, that if you spend a day walking around imagining that the Earth is not moving, then of course it gives you a completely different perspective on reality. You know, you're just driving down the road, you see the cars and trucks driving by you, and suddenly instead of seeming small and insignificant, suddenly they take on a much bigger meaning. That, you know, maybe we are important. Maybe we're not just adrift, you know, like a random mistake in a meaningless universe. We're more like important, and our actions on Earth actually have a difference and, you know, make a difference. So there's that to think of.
The axis of
go ahead.
Yeah, the axis of evil you have mentioned, is it connected with the Great Attractor?
Not as far as I know, but it would be interesting to, for example, map the axis of evil and those dipoles within the CMBR radiation onto the Earth's surface. Because if they are directly in some way mirroring the Earth through its specific plane of ecliptic and equinox points, which would be specific to the Earth, presumably, then we'd imagine that these blobs that I showed you, that in the dipoles and quadrupoles and even up to octopoles, which are all determined by differentials of the CMBR field. You know, so you'd have first, second, third differentials. So that would be interesting to see if, when you map them, do they have correlation with objects on Earth, like oceans, for instance, like Robert Bataille suggests that they are actually just reflections of the Earth's geomagnetic fields over the oceans, for instance, which is actually a real thing. Like the geomagnetic field over the oceans is a lot more intense than on land. But supposing Bataille, who isn't actually well loved in the physics community, I don't think he gets a lot of traction with his ideas, but for obvious reasons in that case. So it would be interesting then to map all of this, the imputated galaxies that I have, including the Great Attractor, and map them onto the Earth and onto the CMB. But obviously, well, from the point of view of mapping anything in the sky into the Earth, it becomes problematic because, you know, the Earth is rotating. So everything it'll just move along as it goes along. But there might be something that's, or alternatively, like if we're saying that the Earth is at the center of the galaxy, then it seems more likely that everything is rotating around the Earth. If that's the issue, then the further out we go, obviously, the higher the speed of the galaxy's rotating becomes. And I think you don't have to go too far out before things are rotating faster than the speed of light.
Superluminous. That's what. Yeah.
Yes, but we're talking about massive objects, because usually when we're discussing superluminous, we're often talking about waves with no mass. You know.
Yeah.
And in Einstein's theory, obviously, anything with mass, like, it increases its weight. So, well, I mean, maybe that's not the case. Maybe it's to do with time, but there is an issue there. And I think there's another author who's out there called Robertson-Janis, who's really popularized a lot of these theories on galactic-centric universe theory and geocentric universe model. And I think he's suggesting that, I think, like, he has a kind of an ether model where the faster things are traveling, well, so that the ether gets denser as you go out, I think. So a bit like how the speed of sound travels through wood at a slower pace than it does through metal, because metal is denser. So light would be traveling faster out there anyway, because when you rotate something, the forces on the outside would cause the ether to become more compressed, more tension. So this light could travel faster out there anyway. So to them, the speed of light is the speed of light that we read here. And so the fact that they're moving at very high velocities doesn't actually matter, because everything remains the same, you know, from their point of view. And from ours, everything is balanced out perfectly, which makes sense, because like we said, with the Earth's surface, no matter where you go on the planet, the speed of light's the same, and the time dilation and all of that is the same. And that is because of the way the Earth is shaped. It's like an oblate spheroid. So the distance out cancels out the rotation and so on and so forth. Because, yeah, so, and that's a remarkable coincidence. And then it makes sense that such a coincidence would expand out from the Earth throughout the entire universe in that sense. So it's not that Einstein is incorrect. It's just that in this model, it wouldn't apply because of the way the universe is set up to begin with. So it was set up with the Earth at the center. And that's why, you know, like, if there was a big bang, a creation moment, it came from like the center and everything expanded out from that. And that is, like, you know, one of the theories suggested of why the cosmic background radiation looks like a mirror of the Earth situation is that it's during that flash of creation, there was a photograph taken, like a 3D photograph of the Earth, sort of imprinted into the night sky and into the universe around it. Sort of like a photograph, like I said. So, yeah. Yeah.
One of the things is that I think, like we mentioned, with the Christian also agreed that Einstein had true solutions. Actually, they only represented the one which less than speed of light, but he had another solution that showed that it's superluminous. And one of the, you know, I think I mentioned, and I can actually kind of, let me see whether I can pull up that.
Yeah, if you could share, that'd be good.
Yeah, let me see.
I'll have to add it to the stream when it's ready.
So let me try to present that.
So I was a bit nervous during that, actually, because there's a lot of information.
Fine. Yeah, it's a very comprehensive. You did a good job, because it's such a vast area of the subject that it's very hard to, you know, really put in half an hour or 1 hour. It's such a huge thing that it requires many presentations. So I think you did a great job in, you know, in putting them together like a summary. Can you see now?
Yeah. Oh, wait a second. I'll add that. Yeah. Okay. Yeah.
See, this is the paper I'm talking about. Let me zoom a little bit more.
Oh, yeah, that'd be great. It's interesting, though. Who are the authors on this paper? This is from a...
let me zoom it So this person, Dragon, is there. Dragon. I think we were talking about it earlier. I'm not sure.
Yeah, it's plausible. Oh, there, that's better. Yeah.
Now we can see, right?
Okay. Yes, relativity of superluminal observers in 1+3 spacetime.
Yeah.
Great. So, I like it. Yeah. Go ahead there, Roger.
So yeah. So if you go down, I had to go there and let me operate it from there. And then I think we have to, you can see that now, right? Yeah. I think he shows somewhere, let me see if I remember it right. The two solutions he says, trying to pull out. Somewhere he's saying, yeah, he does some transformations and things out. There are two solutions. Yeah. So, yeah, there are two solutions possible for the equation. You have to actually go through it to understand. But essentially, he's saying that plug it back, and after we find the velocity composition formula, superluminal velocity, which is a superluminal version of 2. Okay. So, number, 2 is this one. Yeah, this is the one. So this V prime he calculates has two solutions. One of them is superluminar, one of them is subluminar.
Wow.
Yeah.
So what does that suggest?
He just put out from the Einstein himself, but people only emphasized, and Christian was saying that actually Einstein's thing, probably he can translate the German version and then show that Einstein had the two solutions. Somebody who translated into English, only put the solution that is less than speed of light, subluminar thing. But Einstein himself, to be real, I think it may have to do with the real things versus imaginary things, or I'm not sure. But
I remember him saying that. But I've heard a lot of things like that, though, Rajan, in the past, and maybe they're all the same thing. For instance, the idea that we have that light is a constant, and it doesn't change. But then some people were saying, reading Einstein's work, that he wasn't saying that. He was trying to say that light does change its speed according to where it is in the universe. So if it's closer to the Earth, it's going slower, or to a star, it's going slower. But then when you think about relativity, because time slows down when light slows down, it's kind of it's kind of like an equivalent statement. When you could say that the light is slowing down, or you could say time is slowing down. It's kind of one and the same thing, right?
Yeah.
Is that kind of what you're talking about, or are you?
I was pretty much talking about that how you see it, time domain or space domain, and how you interpret that is where the thing is. You can interpret because they appear, it's a differential of time. So one is the numerator, one is the denominator, time, and on the right hand side you have the velocity. Velocity is a differential of space, or the spatial distance movement with respect to time, right? How much it moves, the distance moved with respect to time. You are dividing it. So we are dividing the space by the time. That's velocity is how fast is the rate, how fast it's moving. So because we can interpret that either the time is changing, then in that case the velocity, then the velocity then is remaining constant, but the time is changing, and hence the space is changing.
Right.
So one is constant, or we can say the time, both of them are changing, or only the velocity is changing. So which means that if the velocity is changing, both the space and the time are changing. But how exactly that? So that's a little bit confusing. How does it actually partition between space and time. If velocity is changing, is the space changing or the time changing, or both of them are changing? You can interpret that way. So that's where the whole question is. And this person Dragon, he says come up with the 4 potential and 4 current thing, like very similar to what I'm saying, the 4 vector. So that's why you have to consider the time as 4 vector time matrix, the matrix I was presenting. So I think he's saying that in conclusion, so these are all these transformations, dynamical equations and transformations, connect with the Maxwell equations here. And he says that you can rewrite Maxwell equation for superluminar frame like this one. That's a modification of the Maxwell using superluminar frame. What happens? And then he's saying conclusion, extending special relativity allows superluminar initial observers 1 plus 3-dimensional space-time. So the observer, like I mentioned, the observer, again, I was interested because I was mentioning about the observer physics and also mixed observer in one of the PowerPoint earlier presentations. So they can physically distinguish from the subluminar ones, but we show that they are indistinguishable among themselves, just like all the subluminar initial observers. One of the most challenging and counterintuitive aspects of our construction is that space-time metrics in superluminar frame transforms itself 3 plus 1 dimensional 1. Therefore, we develop the whole kinematics static derivation. Okay. He showed the speed of light is still preserved by the super boost. Position preserving the speed of light may not be considered complete. Conventional. Okay. Expressions of energy and momentum showed that the dynamical theories of least action, including superluminar observers, cannot be based on a mechanical paradigm of classical point-like trajectory. Okay. Leads to a principle of least action based on field theoretical framework of Maxwell's theory. Emergence of field theory. Field theoretic matter waves believe that postulates underlining our fundamental cannot be derived from anything more basic. Showed justification of quantum theory using extended relativity. Remains to be answered is whether tachyons as localized lumps of energy traveling super can physically exist. So that's the question that is raising. So then also quantum field theory, spontaneous symmetry breaking such as Higgs mechanism, fields whose mass squared is negative than broken phase. So he's saying that the mass can be negative. Excited is regarded as tachyons. So there the tachyons are the negative, mass squared is negative. It's not just a mass squared is negative. So the mass is imaginary in this case.
Right.
If you take a square root, then you get imaginary. So the mass is imaginary.
I thought one of the the equations for, was it gravity or some, possibly Einstein's field equation and Hilbert's gravitational field equations, that you could put in like a negative mass in there and it works just.
Yeah, actually the solution, if we put c square root of is about c square c square minus v square or something, right? It comes. So in that case, if the v is greater than c, then you get an imaginary thing. So E equal to mc square, the m in that case becomes negative, right? So when you put in
there'd be different ways of going about it. So I just know the simpler sort of version.
Yeah. So I think that's an interesting thing I find, that actually it's how you interpret all this mathematics. That's what I was mentioning. So what I come to a conclusion is that from observer physics, things like that, which shows mixed observer, right? In relativity also, you are mixing observer. I think we are going to look into that. Emery is also interested. I think we'll be looking. We have already published that why Einstein's thing is falsified is because I think the observer is looking at two people. See, if you are looking at one observer and then change it to another observer, then the results will be different. And Einstein says that no matter who the observer is, in one of thing, at least I think it may not be Einstein himself, but people who interpreted Einstein said that if one observer is in a moving train, another observer is in standing still, and eventually the non-inertial frame, both of them will see the speed of light will the same. Things like that. So it mixes up observers. I think the problem is you have to look at one observer, like I am looking at it, and I am interpreting the two things should be and then you are saying, okay, you are or somebody else is observing, that also should be the same, but it depends on whether it's superluminal observer or subluminal observer. The role is reversed. It's a superluminal observer. Suppose you are superluminal observer, the role is reversed. What you see the time going back. You see the reversal of time. You see the time and space as inversed. So you see the event that's occurring, that I am saying sequence. I think event 1 and then occurring after, event 2 occurring after event 1. In subluminal thing, it looks the other way around. So the event 2 will be occurring first for you if you are superluminal observer, and then event 1 will occur. So it's kind of reversed. Space and time are kind of reverse roles they play. So that is the problem. So if you are saying that superluminal observer and the subluminal observer should observe the same thing, I think there is a mixed observer problem there. I think that's what even quantum mechanics, what he's saying is that superposition, both of them are in superposition. So it looks at, quantum mechanics relativity looks at that, the fact that all of them the speed of light should be the same for everybody. It resolves that way. But the quantum mechanics says that, no, it's a superposition. Both of them are correct or both of them wrong. So I think that's where the differences come back. All the problems, inconsistencies come because of this mixed observer problem. I think if we sort it out, I think vacuum catastrophe and also ultraviolet catastrophe probably could be solved if we kind of separate the observer and seeing that. And that may not be a very easy one, but there may be some easier way to do that. But eventually, it will involve a fair amount of research. It's not like we can talk in one sentence. The solution is not just like that. I generally believe that many other scientists are highly intelligent, highly geniuses. But then it should have been solved, right? Why it cannot be solved is because it involves these minute things where you have to pay attention to the details and you have to expand that little aspect. Like you mentioned about axis of evil, great attractor versus repellent. It takes large amount of time, that suppose we may not have that now, but we have to buy that time somehow. So that's what I'm trying to do, buying that time. And then not to trivialize the problem by saying that, okay, we know that, you can answer it in 2 minutes, all these things. I don't think it's possible. I mean, there are things, of course, there are things that we have expanded to the limit. And these are trivialized things that we may spend hours and hours together and finally come to the conclusion, oh, I could have answered in 2 minutes. Just I missed something little bit here. But I don't think this is the case, because many mathematicians or scientists, and I am actually reviewing something now, and I mentioned earlier, right, one of the Saturn thing about the magnetic field rings. I think we discussed that.
Yeah, we did something like that.
Yeah, I reviewed that, right? And now they have published that. So I will
yeah, I
share.
remember the review. Yeah.
Yeah. So
it was
they have
interesting.
published. Yeah, they have published that. Let me. I don't know. Let me see whether I can. Let me go back and briefly. So you may want to look into that because it's kind of in your area also. I think.
Yeah, do send it on.
Yeah.
Sure.
So I'll pull it out and see. You know, that for you. I think.
Well, I mean, the other interpretation of the Michelson-Morley experiment that revealed, well, a lack of ether. That's how it's sort of interpreted. But another way of saying, it showed that the speed of light was constant. But
can you see it now?
Yes. So, so the speed of light being constant, but another way of saying it is if the Earth wasn't moving, then you wouldn't find a difference either in the diffraction patterns. But what they did find was, I think I showed that paper a couple of weeks back to Christian and yourself. It was wasn't called the Michelson-Morley experiment, but it was the Michelson-Gale experiment in 1925. Do you remember? And basically, in that case, he did find a difference between the interference patterns. So what he found was that it was, he was hoping to find one that would, because originally they were testing for the speed of the Earth around the sun, but then he just looked at the rotation of the Earth itself, so 24-hour, and in that one he did find a difference in the interference patterns. And so it was published in newspapers saying Michelson-Gale experiment is another proof that Einstein was right for some reason. They didn't explain why. But if anything, it doesn't help Einstein's case, because I think a big problem, like if we look at, Einstein was just a teenager or something when relativity was first being discovered, because the Michelson-Morley experiment was in the late 19th century, 1800s. And so he was he was just a teenager at the time. But so a lot of people like Poincaré and Lorentz worked out all of the mathematics for relativity early on. And there was another Irish guy as well called Fitzgerald who figured out the Lorentz contraction. It was originally called the Lorentz-Fitzgerald contraction, as I learned recently, I think from Bill Gady. But so they left him out. So that's a bit annoying, Why they leave out they seem to just leave out Irish people. We can't have Irish people, so we'll just leave it. So I'm going to call it the Fitzgerald contraction from now on, But anyway, all of them got shafted in the end because Einstein just came along like decades later, published his paper, and got all the adulation. And I think the reason for that is because he just stated outright that the results of the experiment meant that light was constant, and therefore time dilation and length contraction, as proposed by Fitzgerald and others, was correct. So, but the thing is that no one had any evidence of it being correct previously, so they couldn't say like outright, "Oh yeah, we just," they couldn't say either way, so they just left it as just in the air. But Einstein was very, he just asserted the fact without any real proof. He used thought experiments and stuff. And then later on, the experiments came forth that sort of, would you say, helped his conclusion, I guess. But for instance, the Haffield-Keating experiment was very badly done and wouldn't hold up scrutiny today. But then the other ones, like one done by Eddington with the eclipse. Often well cited, and of course the results from the perihelion shift of Mercury. So I mean, there are interesting little things there. some would say they're quite big evidences. I'm not entirely sure, but we know that that other people came up with similar ideas prior to that. For instance, there was a guy called Paul Gerber who worked out a method of fixing Mercury's perihelion by supposing that gravity moves at the speed of light. But his results weren't perfectly on the button, you know, using his method. But that could be explained because the measurement of speed of light changed constantly throughout time until they fixed it with the meter. Yeah. So, or it could have just been like bad, you know, measurement deficiencies at the time anyway. Yeah. So there's that kind of thing, but yeah, just asserting that things are one way might not necessarily be the truth, because there's, like, as you say, there seems to be multiple ways of looking at things. And one of the ways could be to say that the Earth wasn't moving in that experiment. And that would make sense then, because if you couldn't find the interference pattern for going around the sun, then that seemed, but could find it for the daytime period, just orbit, then that would seem to suggest that heliocentrism as it stands today is out, you know? And if heliocentrism is out, then that just places the Earth at the center of everything anyway. So it keeps going back to that conclusion, I think. So it's pretty interesting. But like we said, I think Einstein's equations and relativity could apply on a small scale to the quantum world, which is interesting because there's trying to unify them both. But like, as we also talk about, a lot of the problems exist at that scale, trying to unify. So, you know, like you mentioned, the vacuum catastrophe, and others, like trying to renormalize gravity at the Planck scale and things like this. And obviously, you know, theories like string theory do an okay job, or, well, they fix those kind of things. So, and there'd be other, there's definitely other ways to apply, I think, some of Lorentz's and Fitzgerald work and Einstein's work to quantum mechanics. So yeah, it's still useful. Like,
so see, this is one of the things he has come up with, Saturn's protoplanetary. So you may want, I can send this.
Yeah, do send it on to me, but just give me
this is the citation. This is a citation. We can see how Saturn, it's a physics astronomy 2023 715457. So this is a DOI. So this is the reference for that paper. But
okay, I mean,
so
you can even put that into the private chat there if you want, or the public chat.
I can probably put that right now.
So the other thing is, we looked at that a while ago, wasn't it? Back in last year. Was it?
When I was reviewing
early
this
year.
When I was reviewing this, I think I was okay. So let me see. You got it now, right?
Yes, I did. Oh, great. So could you give me a bit of a, because it was so long ago, my memory of it is a bit hazy, but it seems to be about ice particles or something?
Yeah, how he says that the rings of Saturn, you know, is due to the magnetic things. Is due to the magnetic field. It is the operation of the magnetic field that is creating the problem. The structure of the rings, the Saturn end up in the plane of magnetic weight and create a system of rings with well-shaped particles. And how the question of, you know, axisymmetric magnetic field, how it is affected, affecting, you know, affectation of the magnetic field, how the so he's pointing out here the H lines, the rings, deformation of Saturn's dipole magnetic fields by the disk of dense rings. So it's a deformation of the magnetic field that's creating that we see as the ring, you know. as a different ring. So here he is pointing dense and rare field areas of particles, a system of dense. So there's some particles that's being arranged that causes the ring to come there. The magnetic fields are arranging those particles to be forming in that ring. So
yeah, it's interesting. So the rings are a bit like field lines or something. So is that something that could be shown? How do you say, by experimental?
Yeah, he has done both. I mean, he has done calculation,
the
computation with these, right? With these, his mathematical analysis, all this mathematical analysis of the magnetic field. Amazing. And then he concludes that here that the magnetic field is the original evolution of dense rings is due to that. So that Saturn could create stable dense rings by means of dipole magnetic field together with gravitational field. So it's the interaction of the magnetic field with the gravitation field. So
where is his you mentioned experimental evidence. Does he have that?
Well, he's just interpreting, in terms of that. He's giving explanation. I did some of his previous ones. I think he has some experiments he has done. I've not gone through or superconducting. Okay, this is the person. He has done some. Okay, it's mostly explanation, but I think there was 1 or 2 experiments. Let me see. If you look at the
it'd be interesting to see that.
Yeah. I think maybe this one. I saw one of them. I don't remember exactly, but one of them has some experiments he has done. Meissner effect, quantum trapping. Meissner effect. I think here on quantum trapping of particles. I think one of them he has some experiments there. Although he has not put the experiments. I don't remember whether he measurements or experiments. I'm trying to see, so that will be easier. But I think one of them shows the experiment, some measurements, some type of measurements. Let's see, mechanism, third force. Yeah.
Are you looking for?
I think it's included in one of the papers. Some measurements. Yes, included some measurements of these rings here. So then he has replotted. Although these are schematics, but in one of them he has plotted the rings, the actual measurements with the rings.
Well, it's a fascinating area of study, isn't it? There's something about Saturn's rings that are so, I don't know, enigmatic. Is that even the right word? Deeply enigmatic.
Yeah.
There was an old, I think it was a French researcher who had this thing called the Saturn Ring Builders or something like that. Have you ever heard of it? Saturn Ring Builders. Now I find it. I'll just look it up now to get the actual title. But basically, what it was, Ring Makers of Saturn. That was the title of his work, by Norman or Bergrun. I'm just gonna post that in for you so that you have it. But now, I found it always a very interesting concept. But I must admit that having listened to readings of his book and other kind of things, I found it to be a bit dull, But basically, what it is if I post it there, Ring Makers of Saturn by Norman or Bergrun. And so basically, it's kind of related to the topic of UFOs, that he's taken photographs or he's looked at other people's photographs and seen these very strange oblong objects that are kind of moving. And sometimes you'll see a ring forming, and at the end of it, there'll be this like oblong structure as if it's like creating the ring as it goes along. So it's really fascinating, but it's done in a terribly dry scientific way, or just dry in general. Like, I don't know how much total science is in it other than observations, which I'm not even sure if people have concluded if they're correct or they, you know, but it's interesting. It kind of reminds me of, you know, who's the guy who found canals on Mars? Lowry, was it? I think it was Lowry anyway, but it's kind of in that bracket maybe, but I don't think it's been disproven necessarily. It's just overlooked, maybe part of physics history. But I actually have another, if I go ahead and show.
Yeah, another thing.
Yeah. Well, I do have a thing on.
Okay, go ahead.
It is, did I share window? Yeah. This was research I did before on Saturn. So signals from the black cube. So there was this signal picked up by Cassini probe back in 2004, and it was like, you can listen to it as well, but it's looks like that. It was kind of kilometric radiation from Saturn's pole, and then of course we have the hexagon.
I cannot see. Are you sharing?
Yeah, sorry. How am I? I'm not.
Are you sharing?
I'll share now. There, you can see that. Can you?
Oh yeah, now I can see signal from the black cube. Yeah.
Yeah. So you have the different signals. Yeah. So this is the kilometric signal from the Cassini W map, and then here we have the North Pole of Saturn, which is like kind of like a hexagonal storm. So I just sort of was messing around a bit with this, so you could like convert the signal into this sort of structure. And then I was thinking, well,
are you using
what if, like, huh?
Christopher, are you using the neural network type of thing that you are mentioning earlier, or it's a different type of?
Oh, this
processing?
Is entirely different. This is purely just how do you say, like Photoshop, but also, you know, I'm just sort of comparing signals. So here we have the yeah. Here we have the hexagonal storm, and here's the polar transformed signal, kilometric signal. So I thought like be interesting if you could like rotate it, because you can see here at the center there's a kind of a spiral, which, and so if we overlay it with the two, you can see this spiral, and it matches perfectly kind of that spiral. And then this dense storm here matches up with the orange, with this yellow part here. That's actually what I originally matched this image and this image up, and then I thought this spiral also kind of started to match this area here. And then like you can go on. I think like this there's a kind of a line out here where the storms change from being smaller to bigger, and that line is also there. But I mean, obviously there's a lot of noise and stuff that I don't think necessarily. So, and some of it could be kind of pareidolia, like you're seeing, oh well, that looks right, but then do other parts of it. So, you know, that's why I've never really attempted to publish this or anything, because like I don't really feel that it's very strong work in any sense. So that was it. But I do like Saturn stuff. So
it's very interesting. I mean, it has a lot of astrological things also. People, astrologers use a lot to describe our own thing from the Saturn rings, how affects our mood, things like that, even our state of mind in some ways. Our mindset is affected by the Saturn rings, how they form, and it can affect your your performance or how other people see you and things like that. The Saturn rings have a lot of these interactive aspects. In astrology, very important part.
Well, that's true. There's an important fact about Saturn is that its orbit takes 29 years to, it takes 29 years to go around on its orbit. And the reason why that's important is because, well, then you have Saturn return. So every 29 years in your life, Saturn goes back to the same that it was when you were born. And like around that time, people have like really make or break crises in their life. That's why you see all of these important like musicians and famous people, rock stars, who like completely break down around the age of 27. Kurt Cobain was one, Janis Joplin, Jimi Hendrix. There's loads of others. So that some people say that it's all to do with the Saturn return, and people like get really around that time. If you haven't done anything with your life, it's like you just get this really intense, heavy feeling. You have to do this thing, or else, you have to start.
Like I am feeling now. I'm feeling now.
Oh no way!
I mean, I mean, it's not that I couldn't do that, but I was helpless in the 90s to do anything. And then found a way finally a few years ago, especially the ice that I was able to break the ice with by visiting Emmanuel. Emmanuel came on suddenly and then said ResearchGate, and he started interacting with me and saying that, I was reading all your things, and it's unbelievable, the level of Maxwell, things like that. So he started interacting. Then I had a chance. Luckily, there was some other occasion I could go because of marriage of one of our close friends. And so I could go to Greece. And then in that time I said, I just had to reroute a little bit. Then I went to him and then saw him and everything. It was fantastic experience we had. He hosted, and it was like a real presenter or speaker that I was there, and he hosted me and my son very nicely. So with that, it take off, and we started interacting, and I could pull out things from Maxwell, our thing called vortex theory, and then his original work somehow I could pull out. So it was a kind of a benediction type of thing that it showed me that I'm on the right track. Actually, Maxwell original thing, he was thinking about fields, but he kind of took away that, and then he formulated with Faraday's and everything, all these 4 equations. But he was originally thinking about the vortex thing, and there's a lot of literature about that. So if you go back to Newton, Einstein, it's original work, even Einstein, I think that's true. They were thinking differently than what is now, available normal science that we see it. Even Galileo, I think, was different. Although he believed in gravity, but his explanation and what he interpreted and what he was original thoughts were very different. So I go back there and then say, okay, there is a connection there. Maybe do something about the vortex. That's why I came up. I started feverishly working on these things, and a lot of mathematics. I did a lot of different things, and we started drafting different papers, and we sent to a few people that we know, and then they commented. It was good. Until then, there was no real proper interaction. Although I tried to do the science forum, some other 5 science forum or something, but it was not very productive there. So
that's it.
Here it started becoming productive, and we were, at some point I was down because I couldn't find anything. Then he will cheer me up. Then at some point he was down because we couldn't break through something, and so then I will cheer. So back we went. Finally, we came up. I could come up with this. In between, I had done this 2x2 matrix. I looked at it again, and then I say, okay, one of them will represent the vortex field, Helmholtz decomposition. Then I came to the idea that I had to quote something that's called Helmholtz decomposition. I find suddenly, and that one of them could be the vortex field, which is a rotation field. The other one could be the gradient field. So then it makes sense in the field theory that how they split up and come together. And so that case. So let me, if you don't mind, I'll present one thing that I am working on now that we might.
Yeah, well, before we go into that, Rajan, would it be all right if I asked you some questions on different topics?
Yeah, go ahead. Yeah, after that I will just, okay. Please.
Yeah, because there was a couple of things I was interested. Well, I was just going to say some of my questions are kind of just comments, but yeah. So I was going to say, I suppose I should start with this one because it's the first one in my mind. Yeah, so like the way I've been working with two by two matrices as well, and I've been thinking a lot about Einstein's equations, like the sort of Lorentz contraction or Fitzgerald's contraction, as I'm going to call it. Let's see. But yeah, so those different kind of things. And so that all works in with SL23, this special linear group, and they play a role in the fermions. So that's all works well with the 24 cell as well. So, but the thing is, I could like do graphics where I have those cones, they kind of point vectors. It's like a cone going this way and in space, and it just shows the direction of the vector and the magnitude and the direction. So I could like start applying those matrices and warp the space around a point that would be in line with those matrices. So, and with Einstein's work. So it kind of goes back to what you were asking about before, about visualizations of space bending around a point in space. So that's a possibility now that it just came to my mind there the other day.
Oh yeah.
Right. So that might be helpful. I'm also interested in, your work, how it connects with Markulakis's work, of course.
Oh yeah.
Emmanuel's, but so and then Emmanuel's thing is like this torus, right? So
oh yeah,
I was thinking the other day, I kind of forgot what I was thinking about, but it was something like, why not like broaden the, so you have the torus and that's cool, but like there's other kinds of shapes you could use, but maybe I was thinking like hyperdimensional versions of that. So you could look at, you could have like a field that like the electric field goes out, but then maybe the four-dimensional field kind of curls in on itself to form the magnetic field. So the magnetic field is a four-dimensional deformation in a sense of the electric field. It's one plausible thing that could be looked into. Also, I was wondering about the paper you showed had like 1 + 3 dimensions of space of relativity, but you're saying
right now.
You could have other types, couldn't you? You could have 3 + 1, for example. You mentioned that before, but I suppose you could also have like 1 + 6 if you're going into maybe string theory. I don't know. Maybe that's not the right thing.
Right.
But then you were saying that paper had something to do with a 4-vector for time.
Yeah, exactly. No. 4-vector field. No, my thing is 4-vector. Only I have put a 4-vector time matrix. Nobody else has done. I don't think.
Right, because their 4-vector field is time plus space. Like space-time is the 4-vector field.
Yeah, more like electric field, magnetic field, Maxwell things. The Maxwell fields. Yeah.
Well, that is interesting. Yeah, I mean, a 4-vector for time. It's like you say, it's your work. It's quite novel. It's a hard one for me to wrap my head around.
Oh yeah,
because you have different proper time and these different things.
Oh
so, yeah, it's a thing.
Yeah, it's actually falls out of our derivation. See, I believe in derivative formalism, so I derive from that, gauge it, so from there, it essentially starts from the 2 by 2. See, you can think of a 4-vector as a 2 by 2, right? It becomes 4-vector becomes 2 by 2 matrix. That essentially,
Yes, right. Yeah. I can follow that.
Yeah. So the 4 vector is represented as 2 by 2 matrix. The Helmholtz thing also, it's like a 4 vector. So 4 vector matrix. The Helmholtz thing also, decomposition of 2 by 2 matrix. But I am putting the 2 by 2 because now we can solve it, using eigenvalues, things like that.
I mean, I like it as a concept from the, like, you could have like one vector maybe going to the future, another, or another
exactly,
or scalar, one going to the past, and then you could have like imaginary time, like we spoke of with imaginary mass going the other direction, or and I'm quite obviously most of my work is generally about 4 dimensions, how you can use 4 dimensions as 4 spatial dimensions, obviously in my case, to model a lot of quantum stuff. But just something to think about, I suppose. So what were you going to present?
So before I say that, one more thing, I presented my second PowerPoint 2 weeks ago, not the last week, before that, is about world line and the timeline. So the 4 vector can be changed to 2 of them could be world line, which is global. The other one is timeline, like what we do every time. And the world line is something that from the astronomy, from galaxy, money or constellation, another constellation coming to that time aspect, coming into our thing, affecting our timeline. So I think there are 2 ways, which is like we are going from the past to the future, right? And the other timeline is coming from the future to our timeline to the past. So that intersection creates a present, the world line. The present time.
Oh, the present. Yes. Yeah.
The present is actually intersection of the timeline, which goes from past, what we, from our birth, things like that, or even before that, like many centuries ago, my forefathers and occupied. So we follow that history, right? And history is following, right?
Yeah.
The timeline is moving, but from the galaxy, that's or another constellation, another time is coming that I call the world line is coming and intersecting our line. Okay, so the 2 lines, when they intersect, they create a present, and the present is always shifting to the future, right?
Yeah,
continuously.
Well, that's interesting. So it's always moving into the future.
Yeah.
But it could be like, I mean, it's a bit like what I was talking about before about the the chain. You have like catenary curve, where the link in the chain holds up the past and the future. Like the link holds up the chain on one end and the other, but the chain is also holding up the link. And then if you like raise one and lower the other, the link moves along the chain. But then, I don't know. Again, it kind of goes back to no. Keep going. What were you saying there, Rajan?
Yeah. So mainly, what we perceive as the time move, in terms of event, the past is the history, and the present is keep shifting. What we did like half an hour ago is history now, right? We cannot.
Yeah.
Ideally, we cannot go back in time. I mean, the macroscopic time, at least, it is irreversible, right? We are keep moving in one direction, arrow of time, so to say. So the history is the past, and then it's only in our memory, so to say. And like John says, now, the now is always moving, to the future. So that intersection, I had to study a little more. I am trying to study, and it makes sense to be, and also, it tells a lot of things about quantum mechanics, and also relative you can explain, is that the event determines the time. So some event is happening, it makes the time irreversible. That the time is the mark of that event, and that event we cannot go back. Whatever happened yesterday, we cannot go back. We have the memory of that, but we cannot go back to that time. But at the same time, then we have to keep moving, and that's what I call it timeline. So timeline means okay, after a half an hour the most, we have to switch off this, right? we are done with this, and then next week we are doing again another new session. So that's the future. So it's already marked. So we already recorded, that's marked. We want to record, mark, things like that. And that's our history, that's in our memory. And then we'll try to access that memory. Okay. So something in the future may seem like it's repeating some of the history, but that's because the interaction of the timeline with the world line. You know, you can explain that. And even some of the astrological things, I think you can explain that. So world line, you can think of like a global thing. Timeline is a local thing that we explain. Like local and global are relative, right? I can say local, the Earth is local, right? The whole Earth can be considered as local. And the whole constellation, another constellation than our, or another galaxy than Milky Way galaxy, that timeline, that time that comes to us is global, or that's called, I call it word line to separate that. So timeline is what's happening on Earth, for example, and word line is something that's that time that is happening elsewhere is coming to Earth. So these two are intersecting, and that creates the present. So we have a direct interaction of the astronomy or the astrology with our own experience. So always we do that. I mean, the present is a intersection of that. So we cannot avoid that. That's the key thing. So do you want me to?
I think that's a very relativistic point of view as well.
Okay.
That's interesting.
Yeah.
This guy, when you're talking about observer stuff, the big and the small and all of this, it reminded me of this guy's theories, Laurent Natal, I think is his name. He's a French physicist who talked about scalar theory of relativity. And it's a bit esoteric.
John?
Sorry, what?
Is it like John? Scalar theory of everything? John has scalar theory of everything.
Yeah. Actually, I think it's very different, because John is, when he's talking about scalar, he means it in the sense of like a number. But I think Natal here is talking about scale as in size, which is what you're talking about. So it's something weird, like if you have an ant moving along a table, it moves very slowly. But if you were to take a microscope and zoom in on the ant and move that, it looks like it's moving really quickly. So he was saying that relativity must operate also on different scales. So no matter what scale you are, it's also going to turn up there in some sense. But at that point, I kind of lost his train of thought a little bit. I think other people tried to question him on some aspects and found him he wasn't able to really answer to the best of their liking, I suppose. So maybe his theory didn't blossom that far. But I mean, he had some quite cool ideas. Like he was introducing the idea of fractals into his work, and it was very poetic. He even had the idea. It's interesting that I should use the word blossoming, because he's trying to show different things like space-time, like flowers blooming and stuff like that. So he's kind of he's French, so it's quite artistic as well, I guess.
Oh yeah.
So
should I share now?
Oh yeah, go ahead. Yeah, by all means.
Can you see it now?
Oh yeah, hang on. I was just gonna. Yeah, there was some other issues. I did try to do some work on scale relativity at some points. Just the idea of like zooming in and zooming out of like as you travel. Yeah, so like as you're traveling, your metric is changing, because of how relativity works. It's either getting bigger or smaller. So we could think of it as like zooming out of the metric, zooming into the metric. And then that kind of idea, then you have like scale relativity from that perspective, I guess. But so that was it. So go ahead there, Rajan.
Can you let me in?
Sorry, I have to add you to the stream.
Thank you.
Yeah.
Okay. You can see now, right? Okay.
Yeah, that looks very interesting.
Yeah. So I'll just concentrate on that. I don't think. So essentially what I'm seeing here, maybe you can, if you can do the graphics, you are really good, but I am trying to do the best.
I love that. Did you make that?
I made that. I
really like that. I don't think
this is good, right? This is
I like
good, right?
that. Yeah.
Okay. I use the Microsoft.
I like the way it looks visually. So what is it trying to convey?
Yeah. Essentially, I have to kind of rotate it, but essentially what I'm saying is that the 4 vector matrix is like this, right? The one of them is along this line that called diagonal. Along the diagonal, the other one is cross diagonal, right? So you have this vortex field along this one, and the I had to superimpose that or separately the 2x2 matrix that I did with Emmanuel. That's the Helmholtz decomposition. So you have this vortex field here, the gradient field here. What happens is that you can represent the light as the gradient field and the sound as the vortex field. That's what I'm saying. So the vortex field, the sound, I'm representing here. Okay. So these are vortex field of the sound. So they are moving. So they are, this is one vortex field, and then the next one next to it. So they are or at different locations. Like if this is here, then another vortex is here, another vortex is here, another vortex. These are all the sound. This is at the quantum level, close to quantum level. And these are Planck, I call it Planck sheets, because we can think of light as Planck sheets. Like each light, like very similar to what John was saying about Horde, is almost planar, no thickness, right? So, but I think there will be thickness of Planck thickness. Okay. I think that's the lowest we can go. So Christian was questioning that all of them has to be 3-dimensional. In some ways, it's true. Any planar thing has some thickness, right? But that thickness is only, this thickness of this one is only Planck thickness, like H, 10 to the power minus 34 meters or something. It's very. So each sheet is moving along. So H nu, right, is the energy, the Planck energy, which H times the nu, the frequency. So that produces the movement. Each Planck, you can represent as a movement of the Planck sheet. So each light is here. The next moment in time, it moves. So the wave can be represented Planck sheets. I think that's I find that to make sense from the point of view of let me zoom a little more if I can. Let me go back and try to zoom. We can see better. You see.
Light photon. Okay.
Yeah.
So you're go ahead there.
Can you see now? It's a little better, right? Okay.
Yeah.
So what I'm saying is that the light, I mean, I had put this, maybe you can do another graphics with me, but I'm trying to point out for each of them, it's like a light photon or Planck sheet, each of them. That's what I'm trying to bring out here. So, so these are all Planck sheets that moving in that direction, maybe in one direction or something. I can put an arrow, but it may be in both directions. It can be moved. And these vortex things are the vibrational sounds, like vortex loops. They are the vibration.
So these are vibrations in the ether?
Yeah, could be in the ether, but it could be superluminous. So I think that it's a distorted field, like we mentioned before. So you have this superluminous thing, right? A huge thing going on, but they are not visible. They are superluminous. But in that superluminous thing, somewhere the distorted field occurs. And this is happening at that distorted field locally. Locally distorted field, they provide energy, and that energy converts to there's a field, of course, associated with energy. That field dissociates into a vortex field like this one, which is like eventually becomes sound, and a gradient field which becomes like the light or the photon. So you have photon and a vibration. Vibrations are represented by the vortex loops, and the photons are represented as blank sheets here. So what happens is they intersect. They can intersect at some point, right? That intersection, I believe, can create something like a radar type thing. So this radar at the intersection here, they produce radar waves that comes out. So radar, that's what I'm saying. So I didn't want to put it there. So the sound and light create radar structures out of firewall. It kind of a firewall it creates
when
there.
You're saying radar, what do you mean? Like, because radar is what? Electromagnetic radiation.
Yeah, it's actually a bent radio wave, right? Normally radar is called a bending of the bending of the radio waves creates radar. I mean, that's a macroscopic.
Interesting.
Mesoscopic.
So you're suggesting
that Doppler.
The cross section of the super luminous waves with the light waves creates a bent electromagnetic wave.
Yeah, light and the sound. I think the vibrations are. Yeah.
Why would that
happen? Because that intersection.
Yeah.
What happens is, so that what I'm coming to here. It's a very important. I think it's important. So I want to emphasize that. So what I'm coming to here is very important thing about sound and light. Okay. So
when you say sound, you're talking about a superluminal sound traveling in the ether.
Actually, sound is created, and that the superluminal thing is not real. So superluminal is kind of imaginary, or maybe like a dark energy or dark matter, something like that. But the real, it can, with the distorted field, it becomes real. The real is where the sound and light are. In the real.
So is this kind of going back to your sort of metaphysical, like how? Because when I was years ago, when I was trying to break into physics as a concept, I was kind of doing what you're doing. So the first thing I did was to look at optical illusions, because my point of view was that like physics has to create the world around us that we see, sort of like a dream coming into being. Like what is the physics behind a dream,
Okay.
And then so I thought, well, if it's visual, and it's some sort of illusion, like physical reality, then we can learn a lot about what it is by looking at optical illusions. And that's where I found, that optical illusion I was talking about, where it's a sequence of black and white squares all lined up in a row, and the black squares turns into a white square, and the white square turns into a black square. They just switch. Yeah. And then if you put your finger on one square and move it along, you can, it looks like the square is moving across into the future. And that's interesting. Or not into the future, but I mean to the right or to the left, because it can go either way. That's very interesting, going back to what you were saying about how there's this retroactive causality coming from the future, and there's obviously the causality that we experience going towards the future, and then the two intersect to create the present, and we can follow along the present, and oh look, it appears to be moving forward, but actually, so that's interesting. That that we could, because I was thinking when you were talking about that earlier, I was like, oh yeah, that's really interesting. It sounds like an interference pattern. Reminds me a bit of the chain thing that I was talking about. But really, I was like, oh, I know there's something else under there, something deeper, some concept. And so I think that could be it, like getting closer to it anyway. So the appearance of moving through time is also an illusion. Just like I was saying, because the result of that examination of optical illusions led me to the conclusion that light doesn't move. It doesn't travel forwards or back, or it just rotates in place. It is a torsion field. It's switching back and forth between electromagnetism and magnetism, which is a four-dimensional rotation of the electricity anyway. So, as I explained earlier, which we'll look into more, but so that's interesting. So, and then of course Bill Gates, he did a thing on. He also figured this out independently, probably before I did, and certainly published it way long before I did. You know, that light is a torsion field rotating, and that it doesn't move. And I would tend to agree with him. He's also got a lot of things about ropes instead of strings, that gravity is all tied to everything by ropes. Fair enough. Don't need to go there, but it's still probably important, but I just don't see how you can connect it to the rest of physics at the moment with the standard model. It's a little bit complicated. But not to get you too off point there, but yeah, so you understand what I'm saying there?
Oh, yeah.
There could be some interesting...
Sure.
Yeah. What would that entail, though? So, like, if there's this interference pattern being generated by these two light waves, in a sense, coming from the past and the future, and then we're here, we see one moment, appears to be going to the next. I suppose it's kind of back to Einstein's block universe in a way, a little bit, is it? All times exist at the same time, which, when you think about it, is a very deeply mystical. You know, if you were to sit with like some sort of Native American Indian shaman or something and go through some sort of not initiation process, but like a sweat lodge kind of thing, or even some sort of psychedelic process, these are the kind of conclusions you'd arrive at, you know?
Oh, yeah.
So it's interesting that you'd have the same thing coming out of like Einstein's work, and then, which is like so like, proper and scientific and all the rest. Like, you know, it's part of those, like the Royal Society and these kind of institutions, which I'm certain a lot of them do psychedelics these days as well.
Oh, yeah.
Probably have for like many decades. But sure, like how else does someone come up with something like a Lobachevsky in space, you know?
Oh, yeah.
Crazy mathematical ideas.
Oh, yeah.
Which I will discuss probably later on. But go on anyway, Rashan. Sorry for interrupting.
Yeah, it's all right. Yeah, so that's nice input, Christopher. It's very interesting. Not only interesting, but I think it is quite relevant to what we are going to do in the future. I mean, we'll take up on that once we start, joint thing that we are going to publish eventually. But this is one of the things, the joint thing that, you know, I will publish something before that. I kept mentioning observer physics and different things, strong gravity. I think I will put out a paper by myself, short papers.
Cool.
And it, you know, we can refer to that, and then we can all of us, including Gerd and probably Emmanuel, all of us coming together in this one, because the Cottonian is your area, for example. So what I'm saying is information paradigm shifting part. It's a whole thing. It's kind of unified. So before I forget, let me think. I want to go further than the light, and seeing that even the light and sound are form of unified field. Okay, so you have a field, a unified field, and the sound and the light are two components of that. For example, it depends on the medium. Suppose it goes through vacuum, that field splits into the light. It becomes essentially a light field. If it's through a dense matter, like a black hole, densest matter, then it becomes sound. So I think what's happening in the black hole could be just a vibration or sound. Vortex field. Vortex.
Well, now I'm beginning to understand you, because this links to Bill Gates' work. Because I understood that, like, let's say if light isn't moving, then if you put something in between the like, if you block the light, and then you move the object again, the light begins to travel again. So so how can you? It looks like the light's moving. So how can you square that light is not moving when it is obviously moving to everyone's eyes?
Yeah.
So I was thinking it was some sort of wind, you know, that the thing is winding itself out of the ether in a sense, like this, out of the negative negative interference pattern of whatever is there. So, but and so I mentioned this to Bill, you know, and it prompted him to move on to the next point of his presentation, because he was like, "Oh, they figured it out. I better get it out there as quickly as possible." Because he was mincing it, like, or how do you say? He was like chewing it over, like he would just go on, and instead of like getting to the point, he was dragging it out.
Oh yeah.
I know the answer, and no one else does. So but then when he presented his video, he made the very interesting point that I haven't figured out yet. And that was that the light, when it hits an object, what it turns, well, it's not hitting the object because it's already at the object. It's not moving.
Oh, yeah.
But when it gets there, it converts into heat. So when you're talking about sound, which is a vibration, and then heat, which is the movement of molecules, I think what you're really saying is heat. When you say sound.
Actually, I mean, I like
noise. Like noise, like heat. And then maybe the light is the signal.
So
does that make more sense?
See, I want to generalize eventually to gradient field, and I like the Helmholtz decomposition. Eventually, to the idea is that you use that macroscopically or mesoscopically, we see as light and sound. Then I go back to the microscopic picture or the quantum picture, that actually everything you can finally say is either a gradient field or a vortex field. So in that case, what happens is that suppose we are blocking the light, right? Like you mentioned, that becomes heat. That heat is a vortex field. Okay. So it is moving. It is now it can, so the light cannot move. It immediately changes to heat, for example, heat, or I like to call it vortex field. So the gradient field becomes a vortex field and it continues on the other side, okay, as vortex field. And then you have the gradient. So I think the interference we see is because of the intersection of the vortex field and the gradient field. So that's why we see.
I mean, well, if you have if you look like at turbulence, in liquids or in air, it's a lot of vortices, isn't it? And so,
like a smoke ring, for example, smoke rings. Suppose we put smoke rings and a gradient light. If you intersect that, you will see, in some sense, depending on the angle, things like that, interference pattern. In another sense, you can see diffraction pattern. If it's more, I can say the difference is multiple objects. If there are multiple objects, you get diffraction.
Right.
If it is two objects, just two objects, you get interference. If it's more than two objects, you get diffraction. So that's the difference. For me, that's the difference between diffraction and interference. That is like that's the grating, right? You have many different atoms.
It goes back to a lot of what John was saying about interference patterns, vortices and stuff. I mean, certainly if we look on Earth, when the sun is heating a region of the ocean, you have a tropical storm, then you get these vortex tornadoes and stuff. So there's definitely heat, and vortices are a thing as well. So yeah, it is interesting. I wonder where you can go with this, or are there vortices?
I want to ask.
Go ahead.
I want to ask John, but he's not coming back. But in any way, at some point, if he comes back, this is a question I had. This is one of the questions I had. If he had come, I had that actually the difference. What is the difference between interference and diffraction? And I have kind of. Maybe I can pull out. So this is the main thing. We will pick up on this later on once I develop. But that's one of the main points. I call it the E-circuit vibration and discontinuous. Again, I'm working something called E-circuit that I developed. That I mentioned the word line and the timeline, right? When they intersect, they form something called E-circuit. E-circuit is something that it's like convolution of that, and immediately deconvolution occurs. It's like scrambling and descrambling of signals.
When you're talking about convolution, are you talking about
configuration?
But remember the thing you're saying,
yeah. When it crosses, when they intersect, they form like a firewall or something. That's E-circuit. That's convolution. Then it dissipates into radar. That's deconvolution.
Also, convolution is to do with distance. So the distance between one signal and the next is the, like the Euclidean distance or whatever between the two signals. It's also dimensional reduction as well.
Yeah. It's a short distance, right? It's like a contraction. I mean, like the distance becomes smaller. They are very close interaction, right? So you have both.
Well, no, but I suppose it depends what you're convolving. If you have a signal and the signal itself, and you convolve the two signals together and they're the same signal, you'll get zero because the distance between them in terms of their difference is there is
exactly. That's what I'm saying. That's what I'm saying. So it becomes zero. That's why it collapses, right? It becomes zero. And then from there, like that, from there, the inverse operation or inverse transformation occurs. That's deconvolution, inverse transformation. Then the signal starts again spreading out. So they become zero. Then they split up into positive and negative signals, whatever you call it. And then they start moving out.
Yeah.
So
interesting.
So the other aspect, what I was saying, the question I had, I don't know whether I can pull up that. I don't know whether it's enough time, but I'm trying to see whether I can.
Well, I mean, that works with the idea of a wave not moving as well, doesn't it? Or like
so your idea, it goes back to your idea. Anyway, we'll discuss. I think we may have like another 10-15 minutes. So
fair enough.
I can bring out John's. I'm trying to pull out the question I had. I'm trying to see maybe I can pull out fast enough that I want to bring out the question I had for John that we can discuss. I think even without John, I think we may have sufficient knowledge to discuss that. But at some point, if John comes up,
you might also be able to email him questions.
I want to do that.
Or through, or better yet, through ResearchGate, just drop him a message. Or one of the other.
Yeah, that's a good idea because he's still communicating. So I thought that he will go into his retreat and then he will, I thought, let me see. At some point.
Well, I think that's really interesting what you're talking about there, Raja. It's coming alive,
Oh yeah. That's a lot of things are coming together, but it's not that we can, like we mentioned, many people are now expressed that we cannot give a one-word answer or something to this, But at the same time, we want to reduce it to the minimum level, to the level that I think a lot of that can be reduced. I mean, no question about that. Anyway, I mentioned briefly. I want to take up too much time. So next time, I will try to pull out the question I had for John.
Well, when you think about do that another time then. So, but when you think about it, if you have a wave that's up when the other one is down, then they cancel each other out. They become zero.
Yeah,
which is the opposite of the convolution, because when in a convolution, when they're both the same, they become zero. But this seems to be the opposite then.
Yeah.
Also, it shows that you can have a convolution that is directly 90. Because if you take the dot product of something, if the two vertices, if the two vectors are going in the same direction, it's 0. But if they're
no dot product, no. If they're same direction, dot product will give you 1.
1.
Yeah.
Oh, 1.
Cross product will give you 0. Cross product.
Right.
If they're at 90 degrees, cross product will give 1. If they're the same direction, cross product will give 0. Dot product will give 1.
Oh, okay. So right. So the same. Yes. So then you're talking about dot product, not cross product, right? With an interference pattern.
Yeah, that's an interesting thing. That's something we can look into. I think that may explain a lot of things. That simplifies a lot of things. How the field splits into light and sound. Then you can also combine back like a torsion field, things like that. And then what Alexei was saying about his field, about his fifth thing that he was talking about. So why it travels so fast? For example, superluminous. How does it become superluminous? When it's split, right? It can, when it is splitting, then the light and the sound, it has on finite speeds, right? Light has speed of light, and that sound has its speed, and it can become supersonic, things like that. But when they combine, they can be superluminous, right? They can become superluminous, but they are one field.
I'm not entirely sure about that logic, but like, what is the speed of heat? It depends on the material, right?
No, not necessarily heat. See, initially when they are together, they're superluminous, and at the distorted field, distorted field could produce heat, for example. But the distorted field gives additional energy, that splits the original field into light and sound, and the light itself, now the light by itself is traveling, right? Now once it's split, light itself is traveling, then it hits an object, then it becomes heat. You know what I mean?
Okay, but what about, well, there's a couple of things there, because you have this combined field. So you have a combined field. Well, are you saying that, like, if light is traveling through air or some medium, is it generating sound? Does light make sound?
No. But the light, if it's embedded, it can convert into sound. Like Raman spectra has shown. Raman spectra, they talk about phonon, which becomes eventually sound. Phonons are not the same as sound, but the photon and the phonon interaction, the photon can convert to phonon, the phonon can the vibration, and the phonon can.
Could you give me a reference to that, like a paper or something?
Yeah, in the Raman, I had to look up one of the Ramans. I used to do Raman spectroscopy for diamond when I was trying to make diamond room temperature with a scanning microscope, and then I went through some of the literature of the Raman spectrum, and we had to probably do some research on that. And one of the things he talks about, how the phonon, how the spectrum, you have the photon spectrum that becomes phonon spectrum,
right?
Can be explained by phonon spectrum vibrations. So I think if the light cannot travel, it converts itself to either heat or to these phonon vibrations.
Oh, interesting. I don't know anything about this, Rajan, so I'm gonna have to study on that. That sounds really interesting.
I think we have to go through a literature. Some of them are available, but I don't know whether anybody has looked into the fact that the gradient field, the light can be explained as a gradient field, and that becomes a vortex field when it hits an object, when it is embedded by an object.
Okay, and then, well, that's an interesting one. Yeah, so like we were saying, that's a potentially good research avenue. So also, I was thinking, you're talking about this vortex. Of course, that is a torsion field, right? Because I mean, you can just rotate the vortex, and it looks like it's moving in or out in the direction. So there's definitely something there in that sense as well. But
so it makes sense to what you are saying, that something like moving, like black and white dot. It's actually not moving. It's only changing that black to white dot, white. So it's as if it give illusion that it's moving. It's kind of, I think it kind of very similar thing that torsion field can create that illusion. I feel it. The torsion field.
Yes. Yeah. Exactly. So that's, yeah, it's interesting in terms of. I think there's like something there, but like there's a block.
We are all coming together in something, but we have to find a common area, of in this how everything comes
there's like I can see what you're saying, but it's like there's like something there, but it's like on the tip of your tongue. You just gotta like reach out and grab it. But I'm not entirely sure what it is.
Yeah, I mean, it takes a while. We have to do some more research to figure out these things. But I think the unification then comes there, and the gravity also comes into the picture, like I was mentioning. That's why I want to publish about strong gravity, weak gravity. Like you have an open string, that will be like a weak gravity, and closed string or loop, that becomes strong gravity. And then combining these, it's kind of concept from that string theory, but then we can explain the gravity in terms of that, finally in terms of the vortex and the gradient field, that how it becomes gravity when they intersect. The gravity, how does it appear like it's attracting?
Oh yeah, well, that's an interesting thing. It's like this kind of idea of hypnotism.
Yeah.
So like when the spiral is rotating around and around, it looks like it's going in or out.
No doubt.
Like hypnotizing. Hypnotizing you, and then also you get these kind of like from a visual optical illusion kind of thing. Then when you look at a wall, it looks like it's coming out at you or going back.
Oh yeah.
And then these like within the optical sensors of the brain, and because there's a lot of mathematics going on in there, like log Z transformations, Riemann transformations and stuff, mapping to the reptile part of your brain, the edge detectors. And so that's where we get a lot of these, these visual experiences from psychedelics and stuff, where we see the rotating vortices, and then even when we meet with people where we have a very strong connection with them, like some sort of resonant feeling, or even I'm not even too sure, but like certain experiences that resonate with you, you can see this kind of everything feels like it's one, and like coming together or growing apart. So there's, it's interesting. There could be something there about a resonance and an attractive force that comes out of like an emergent phenomenon kind of aspect, which leads into some sort of vortex, like that. This idea in mythology where you have the center of the vortex is a passage into another world. So. And that's why the spiral is often depicted as, Alice in Wonderland falling down the spiral hole into a different dimension.
Wormhole, things like that, are also very similar. I think the wormhole could be like a torsion field, like a combination of both the vortex and the gradient field coming together.
This is it, of course, because the torsion field could create visually and therefore in reality a kind of a gradient, which would be so almost like a quasi particle then, in the sense that it's not really there, but because it's there, it just is there.
So another interesting thing is the group velocity. Like if they are combined together, and I think somebody proved that group velocity can be greater than individual velocity or something. There is a proof somewhere.
Right.
The group velocity can be greater than individual velocity. So it makes sense. So if you have combined field, combined field becomes like like you mentioned, torsion field. So torsion field, let's say torsion field is a combined, or the light plus sound, or what I call the vibration together. I like to call it gradient plus vortex together. So in general, and that field together, that's the group velocity, the group field. We can call it group field. and the group field will have a velocity greater than either of the one, either the light or the gradient field or the vortex field. It can be greater than either one of them, or maybe, so which means that you can have speed greater than that of light.
Right. Well, that's interesting. I'm finding this is new information to me. Yeah, I think I have heard this before, though. But thinking about it from the perspective that we were just talking about, so you have a velocity of each individual particle, and then you have the resonant velocity of all of them.
Yes.
As a group velocity. So then we can talk about velocity as a kind of a waveform, which I think kind of links to what Gerd has been talking about a lot, about the waveform of the universe. So, it may be in a different way, but resonant velocity. So when all of the velocities join together, they're more than they were, right? They're like reinforcing each other.
And then that becomes superluminous. So the torsion field can be a superluminous thing, as I'm saying, or the superluminous thing could be a torsion field, essentially.
Okay, I'll have to think about that. Yeah, that's new. That's entirely new to me. So I'm gonna have to. What's the word?
It's about worthwhile thinking, and then
meditate on it.
We may find something breakthrough there, and we can publish something together, because Emmanuel will be quite interested, and then all of I think Christian also talked. Gerd also is talking. So and you mentioned specifically about torsion field. I think that's an excellent idea, Christopher. So
great. Well, there's a huge amount there, and I'm just sort of now kind of grasping what you're talking about. It's taken 2 years. I knew it would take a while, but that's good.
I think we may come up with something real breakthrough. Well,
even if we don't, it's going to be fun, interesting discussion. I'm going to take this now and sort of I'm going to rewatch the video and make notes, and
if you can edit the first 10 minutes, we don't want that. If you can cut that somehow.
Well, we're not going to edit this. This broadcast goes out live, so.
Because the first 10 minutes.
I can re-edit. I can re-edit live videos so that they're more concise.
Okay, and then remove the other one. And remove the other one.
No. I won't remove the live versions. The live versions are just live.
I thought that because it has some. I thought I should be careful more in the future, because I was seeing some private things that is not necessary for everybody to see it.
Such as
my own thing.
Well, you can.
When I was searching, a lot of other things came up. My email and other things came up. Other things that it comes up in my search. What happens is when I put that, other things come in.
Yeah, I didn't notice anything, but
anything.
Well,
if you notice that, if you can.
I didn't notice that. Like I can't edit that out of a live stream. That just goes out live.
Oh, okay.
So if you want me to, tell me which live stream is affected. Is it this one or is it all of them? Is it the previous one?
No. The previous one is previous one. What happens is the first 5 minutes or 4 minutes or so, we are just testing. So there is nothing. So people will see that it's blank. A lot of it is blank. So if you can edit that out, that will be good. In this one, 10 minutes.
So I'm not going to edit the live streams, Rajan, because that's a live stream.
Or cut it out. Can you cut out the first 5 minutes or 10 minutes? Is there a way to?
I haven't noticed. Are you saying it's just black?
You don't have to edit. You don't have to edit. Just cut out the first, 5 minutes or 10 minutes.
That's the same thing as editing. Cutting out is editing. That's basically what the word means. But what I will say,
you don't have to do the other things. Other things can go on. What happens after that, you don't have to worry about it. You can just keep it.
Well, I'll have to, like, when I looked at the stream that we uploaded, or we didn't upload it, we live streamed last week. There was no black.
There's blank. There's a blank.
How long does it last for?
Let me show you.
Okay.
There's a blank blank these things that's coming up for a few minutes. There's nothing. I'll show you here.
Okay, well, I think a lot of people though are they're kind of savvy enough about live streams that they know to like
okay,
flick on, you know, until they get some picture. It's not a big deal. Usually, well, what we could do is have some sort of graphic or image instead of a blank screen. If you prefer.
Oh yeah, that will be good.
Okay, but that's if you can find out how to do any of these things, that would be a help as well. I'm sure it's not that difficult, but just search StreamYard, and then anything you want to change, like if you want to change the powered by StreamYard thing up there in the corner as well, we can get rid of that. Although I'm happy with it at the moment. Okay, so that's 2.5 hours, Rajan. I think we'll
the right time to stop right now.
Cool.
Great.
Cool.
That was fantastic, Christopher. Your presentation was really great. I enjoyed it, and then I think we'll pick on that. Because there's a lot of things in there. It's quite dense. We'll pick up on that later on, and I'm sure that other people also will have Q&A, kind of a Q&A later on about that also. And then
great,
we'll
I mean, I wasn't thinking there'd be like a huge amount of Q&A for it, but I'm glad that Gerd was able to see something in his work that were related to mine. So that's really cool. I wasn't really expecting that. So I'm thrilled about that. It was really great to have the opportunity to present that to you guys as well. And just because I worked on that for my master's degree.
Oh.
It wasn't my like thesis or anything. It was just an assignment.
Oh,
but it just kind of sat there. I only got halfway through. And then because I had to do this presentation, I went back to it. And then I did the other half. So, you know, the way I imputed where the Great Attractor was. Then for this, I just went back and I imputed the other space. And then I noticed, well, there's nothing there. It's empty. So I was like, well, maybe that's the Great Repeller, like, you know.
Oh, that's a very interesting concept of repellent, because from the point of view of symmetry, like Noether was Noether, Emma Noether, right? Talks about symmetry, that there has to be symmetry always balancing. If there is a positive, there has to be a negative, things like that. I think that makes sense. So if there is an attractor, there has to be a repeller or what, or repellent.
Yeah, repeller. Yeah, exactly. I said the word repellent, but it's definitely
repeller, attractor, repeller. So it makes sense because, you know, it balances out that way, but they don't cancel out. You see that? That's why I believe
they're opposite ends.
They're chiral. Like left-hander, right-hander are symmetry, some kind of symmetry, but they don't cancel, right? They don't cancel. Yeah. I think that may be so attractor may be one chiral path, repellent maybe either left-handed or right-handed, something like that, and they don't cancel each other. That because it's a chiral symmetry rather than, you know, positive negative symmetry. You know, positive and negative symmetry probably could cancel, but I think more like the universe has chiral symmetry. There is left-handed and the right-handed type of thing.
Okay, yeah, that makes sense.
So they don't cancel. So it probably will eventually solve the problem of matter, of why, you know, the big thing is why there is a asymmetry of antimatter matter, because antimatter and matter, they have chiral symmetry, not, you know, positive negative symmetry. So
you think so? But
I think.
Like, well, then maybe they're chiral to a small, tiny degree or something.
Tiny degree, yeah. So tiny degree enough. You need only that much, right? What is like phase angle? You know, it's a phase angle difference.
All right,
tiny difference.
Tiny difference. Yeah, okay, that's interesting. Yeah. Well, I'm definitely going to look back on this. And
we'll move on.
Yeah. Okay. Nice to see you again, Raj.
Thank you very much. Yeah, until next time. Yeah, we'll get new link, right? Okay, thanks a lot.
New link next weekend.
Okay.
See you later. Bye.
Have a fantastic week. Thanks. Thank you.
So I'm going to end this broadcast now.